All right, recording's on, y'all. So thank you all for being here. I know it's weird. This is a first for me having a review session Friday instead of Sunday, but I don't know if y'all can tell. I'm in a hotel lobby right now. I'm in Maryland for a wedding, and so I appreciate y'all being flexible, meeting on Friday, and then for everybody who's watching this video later, thank y'all for still signing up and getting a recording. So, since I'm behind the eight ball today, I sent out the email this morning for the documents that we'll go over today. We're mostly focusing on fall 2022. Pretty much we're going to use that as a pacing guide. We're just going to work through those questions. I'll go off on tangents and explain things more deeply if need be. I also have a second exam just in case we need a second question on polar and non-polar molecules or ionic compounds. And then, of course, I have a lot of random questions in my brain so I can always think up of new practice problems. The next review, back to Sunday, 10 a.m., day before the exam. So the next one is, next exam kind of stinks for y'all because it's the Monday before Thanksgiving, but that's 10,000 times better than the Monday after Thanksgiving. So that's a silver lining, right? So we'll be planning on doing another Sunday review. Sunday, virtual, 10 a.m. on the 23rd. Registration is already open if you're gung-ho about it. Usually at this time, I'm always like, oh, by the way, I'm a private tutor and I'm trying to tutor more people. But to be honest, I can't really handle many more people. So if you need private tutoring, you can reach out to me and I'll try to point you in the direction of somebody else. But I really can't handle too much more tutoring, except for if somebody's really desperate. I know some of y'all are on this list already, but if you need somebody, I do have a last minute cancellation list that I send out an email to. It's like, hey, I have a session in 2 hours. Does anybody want it? So if you want that info, shoot me an email. I'll be, let's see. Did just say that I stopped the broadcast. So I'm going to rebroadcast that. But there'll be a recording for this video. It will probably be, I'm trying to reconnect my iPad. Let's see. I'll send out the recording today or tomorrow. Cool. Let's see. Can y'all still hear me and see me on this? Cool. In which case, it's just my iPad's Wi-Fi going out. Let's see. Anyways, while I restart or try to reconnect the Wi-Fi on my iPad, just I've never done a review session from a hotel lobby, so if there's any technical difficulties, stay on. I will try to be back as soon as possible. It may just involve me swapping to my hotspot, whatever. So if I just peace out, don't be too alarmed. I'm trying very hard to come back. Okay, cool. All right, my iPad's back in the lobby. Okay, cool. Slowly coming up, but while this is taking forever, because I also have an ancient iPad, we're going to start back all the way question 1 from fall 2022. And looking at that question, it's talking about atoms and bonds. Because remember, we started off talking about bonding theory. We focus a lot on covalent bonds and ionic bonds. What's the difference? What's similar? What are they doing with their electrons? Blah, blah, blah. So, let's see. All right. Lauren, can you still see my iPad? Or now can you? Okay, so all right. All right. So question one, it says, consider the formation of a bond between two atoms. Which of the following statements are false? Which of the following statements is false? I'll always screw up on that. I'll look for what's true. Energy is released when bonds form. That's true. So like not the right answer. I think that screws up all my biology majors. We always are told in biology that when ATP breaks into ADP, it releases energy. What they don't tell you about in biology is that's like 20 chemical reactions in one. I think you'll learn more about that in biochemistry. So in just Gen Chem, we say it's released when you form a bond. And in order to break a bond, I think about like trying to break a stick. I got to put energy into breaking a stick. So endothermic breaking, exothermic forming. All right. There's repulsive interactions between nuclei of two atoms when interatomic distance is shorter than the bond length. That is true. Why would there be repulsive interactions between the nuclei? Because nuclei are positive. They're protons, right? And positive things don't like other positive things. So if atoms are too close, the nuclei start like pushing away from each other. And then it's like a spring. If you compress a spring too much, it wants to expand out. Also, if you start to pull a spring, it wants to pull back in. There's like very much a set bond length for everything. So that's true. The greater the bond dissociation energy, the more stable the bond. That's also true. It takes more energy to break a bond, the more stable or strong it is. And then lastly, this is the answer. The bonding electrons are shared equally in the H to Cl bond. That's talking about electronegativity and polar bonds and nonpolar bonds. I think the idea behind this is a covalent bond. I know that because it's two nonmetals and they're sharing electrons. That's what co in covalent means. But one of them's much more electronegative than the other. Remember, that's a periodic trend that goes up and to the right on the periodic table. And so chlorine is more electronegative. So if I was to write out the bonds, I would say chlorine is more electronegative. So the electrons are being pulled in like this game of tug of war towards the chlorine, which makes the chlorine slightly negative because it has extra electrons, and hydrogen slightly positive. So that's a little sneak peek into polar bonds. Does anybody have any weird or like just broad questions about A, B, or C? All of those were like, I don't know, they're very long.
And then today, right after class, I'll be in my office for about an hour, and it'll be more drop-in style, so just bring questions you have.
Did you know that? Okay, cool. I'll see. All right, question number 2. If nobody else has a question, we can go on number 2. Which of the following are covalent compounds? I didn't mean to cross that out. I meant to highlight it. Cool. So there's sort of like this unwritten rule that if you're just looking at a picture, we're assuming that this is at room temperature. So that's like a big key thing. Unless you're told these part of the diagrams are at 1,000 degrees Celsius or negative 20 degrees Celsius, we're going to assume room temperature. And what tends to be what at room temperatures? So some key, I think my Wi-Fi, my iPad lost Wi-Fi again. So I doubt y'all can see what I'm writing right now. No. Okay. Anyways, while that's getting back on, I'm just going to talk. So some key differences between ionics and covalent compounds. Covalent is sharing electrons, and the best way to find covalent bonds is when you have two nonmetals next to each other. Hydrogen and chlorine, oxygen and nitrogen, blah, 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 blah. All right. Ionic is going to be metals and nonmetals together. I'm going to simultaneously try to work on bringing my iPad back up, but ionics are metals and nonmetals. There are some weird exceptions, though. For covalent, I want you to also know that metalloids and nonmetals make covalent bonds. Silicone tetrachloride. Silicone is a metalloid, so that's a covalent bond. And then, for on the ionic thing, like, honestly, I'm not like upset if you just like look at the very first element and if it's a metal, it's ionic, usually. With the exception of if something starts with NH4, ammonium. Even though those are a whole bunch of nonmetals, is a red flag for, oh yeah, that's ionic. And so I bet you they'll try to trick you with that on the exam. All right, my iPad has Wi-Fi again. Let me try to reshare my screen again. Some other big differences between ionics and covalents is what those molecules look like. And this is where, like, this is how we're going to answer this question. Ionic compounds, pause, let me see. Nice. Okay, cool. Ionic are going to be these lattices. When I think of lattice, I think of like a garden lattice, which is like when you put a whole bunch of like sticks on top of each other and like a trellis that vines can grow up. So I think of lattice as a pattern, right? And so ionic things are going to be solids at room temperature, and they're going to have these lattice patterns. But covalents are usually going to be liquids and gases at room temperature. So you just might have like this molecule floating over here, a molecule floating over there, molecule floating over there, whatever. So that's what we're using in this problem. Which of these are covalent compounds? My guess is only number one. Mostly because I can tell that that's a gas and it's individual particles, not this pattern of positive, negative things. Cool. In these types of questions, even though we didn't use it here, another really important thing is to look out for the ratio of black to white. Whatever this molecule is, if they like threw out random chemical formulas, I know it'd have to be a 1-to-2 ratio of atoms. So like this could not be N2O4, but it could be NO2 because that's just a 1-to-2 ratio. So I'd also be looking out for that. And then another thing I've seen on an exam before is look out for atomic radii. If they were asking like, hey, which chemical does it make sense for compound 2 to be? You would want the white spheres to be the bigger atom. So don't forget about atomic radius from the first exam. That could be a trick that they throw in there. So these pictures I'm looking at are solid liquids or gases, ratio of black to white, size. And that's like some key things that we'll throw in there. Does anybody have questions about number 2? Cool. All right. This is just a different way of talking about what we've already talked about. Remember, ionics are usually solids at room temperature, which means that they have to meet at a much higher temperature before they boil or melt. And covalent things are usually already gases at room temperature, which means they already boiled and melted a long time ago at a much lower temperature. So which of these are covalent? It's probably the one with a really low melting point. Honestly, that boiling point's like, that would like, that's hotter than boiling water, but still, like in the grand scheme of things, when you compare 146 and 2000, 1500, they're still pretty low for a boiling temperature. And so, for that being said, I'm going to go with C. That's probably the covalent compound. When I think of ionic compounds, I think of them, if I want to melt an ionic compound, it has to get like lava hot. We literally call it a molten ionic compound because it's like glowing red hot. like lava. So that's what's going through my brain. Cool. So number 3, just a different way of talking about it, but does anybody have a question about ionic versus covalent stuff still? There are some other things that only apply to ionic and only apply to covalent. We only talk about lattice energy when we are talking about ionic stuff. But when it comes to covalent, something that's more unique to them is like, that's where we like to talk about polar bonds, Lewis dot structures, and intermolecular forces, which is way down the road for this test. So we don't really talk much about ionic or like bond polarity for ionic compounds or Lewis dot structures. Speaking of what's unique to covalent bonds, here's bond polarity. We talked a little bit about this in that first question, but the way these symbols work is when you have 2 covalent bonds, let's say A and B, the more electronegative one. What is electronegativity? Pause. If you don't know what electronegativity is, or if you don't know what any important sounding chemistry word is while you're studying, you should probably stop what you're doing, go to ChatGPT for 30 seconds and say, explain electronegativity to me. And if it doesn't make sense, say, explain electronegativity to me like I'm a 5th grader. And that's like how I use ChatGPT. The other day I was tutoring somebody at a different school and they were asking about like quantum mechanics, like really intense stuff. And I was just like, hey ChatGPT, explain like Schrodinger's wave equation to me like I'm a 5th grader. And like it made more sense than it used to. So that's just my tip for chemistry and life in general. You keep on seeing a word that's important, that seems important, but you like keep on just glancing over it and say like, hey, I'll learn about that later. Stop what you're doing and like, it's called the Feynman. It's one of the facets of the Feynman technique, which is a really famous guy who taught people how to learn. Anyways, electronegativity is the tendency to pull electrons towards it. So if the B is more electronegative, the electrons are being pulled towards it. And we know electrons are negative, so that would be the slightly more negative one. That would be the slightly more positive one. Okay, sweet. So what is the best symbolic description of the bond between iodine and fluorine? Well, they're 2 nonmetals, so covalent, and it is polar. Fluorine is the most electronegative atom out there. I do want you to know that. And so, like, no matter what, it is pulling electrons towards it. So A is the correct answer. C could look like the right answer because, like, most people are kind of confident that it's not ionic, but it's labeled wrong. So be careful about that. Anybody have a question about number 4? Okay. Sweet. Who's more polar is just which one has a bigger discrepancy or difference in electronegativity. So let's look at pair 1. And with a periodic table, I would want every one of y'all to be able to look at it and tell me of these 3 atoms, nitrogen, oxygen, and phosphorus, who's the most electronegative? And after you look at the periodic table, I hope that you would all agree that oxygen is the most electronegative. So like oxygen is this electronegative. And nitrogen is really close behind versus oxygen and phosphorus. I guess in this made up chart I'm making, that's like levels of electronegativity. And the more polar bond is the more lopsided thing. Think of this polar bond as a game of tug of war, and the more lopsided the strength is, the more the electrons are being pulled in one direction. So does it make sense that oxygen to phosphorus is a bigger difference in electronegativity? Like literally, if you're in a math class, I'd say delta EM, difference of electronegativity. And therefore, that would be the more polar bond. Anybody have a question about that? Cool. Same vibe with pair number 2. Phosphorus is, or fluorine is what they have in common. Fluorine's super electronegative. So the one that's more polar is going to be the lesser electron, or like the one that causes the bigger difference. I do need to pull up the periodic table myself. Let's see. And selenium is less electronegative than bromine, so this one should be the answer. Cool. Anybody have a question on number 5? Is everybody cool on how I could tell who's more electronegative in all these cases? Cool. Sweet. The next thing that I want to remind you of is that naming ionic and covalent compounds is pretty different. I think most people get the hang of naming covalent things first. Covalent things are like you say the element, so nitrogen and oxygen or whatever, and then you make the last one end in "ide," and then you throw in these number prefixes: mono for 1, di for 2, tri for 3, tetra, and then it's like all the polygons: penta, hexa, hepta, octa, nona. Okay. Now, ionic compounds, the rule sounds easier, but there's a little bit more to unpack. This is an ionic compound. I know because the first thing is a metal. For an ionic compound, you just say the name of the cation and the anion. So I know this is the magnesium ion with the nitrate ion. Now, I did just give it away. You do have to know the difference between magnesium and manganese. So they're trying to trick you on that. But nitrate, you're not going to find nitrate on the periodic table because there's a list of polyatomic ions that you need to have memorized for this exam. My recommendation is not to learn them for this exam and forget it the next day, because the polyatomic ions will show up on the third exam as well. But yeah, so like this question is testing. Did you memorize the polyatomic ions? I think I might have a list of the polyatomic ions. Let's see if I can find it in less than 10 seconds. All right. This is probably from a couple years ago, but this is the list I have that you need to know. So you're supposed to know, let's see, nitrate, that's NO3 minus. Cool. So that's why here, here, here. The answer should be B. Side note, you are supposed to know that magnesium has a +2 charge. That's based off of where it is on the periodic table. Does anybody need me to explain how I know that magnesium had a +2 charge and not like a +3 charge? I know the first person to ask a question is kind of awkward, but hopefully once somebody breaks the ice, if anyone has questions, I'm happy to answer them. I'd prefer to answer questions than just kind of speak to myself for 3 hours.
Could you explain how it has a +2 charge, please?
Absolutely. So it's all based off of number of valence electrons. So before you can even, I would say before you even think about ion charges, you should be comfortable with the idea of valence electrons. And so here's how that works. Valence electrons, let me do that color coded. So valence electrons goes 1, 2, and then it skips it kind of stalls out at 2, mostly for the transition metals. Then picks back up 3, 4, 5, 6, 7, 8. So, Ava, this is how I figure out how many valence electrons I have, which is related, but maybe not the same number as ion charge. So, things that have more than 4 electrons, they're like a little bit short of having a full octet. Remember, octet means 8. And so things with 8 valence electrons are actually like spot on exactly where they want to be. So they usually don't make ions. They usually don't bond at all because they don't want to. But something with 7 valence electrons is 1 electron short. So they want to add 1 electron. And this one is backwards. Remember, electrons are negative. So if you're adding an electron, you're going down or becoming more negative. That's why things with 7 valence electrons usually like to have a -1 ionic charge, -2, and -3. So that's those 4. And then things on the other side of 4, they're actually like, it would be less work for them to shave off a couple electrons than add them to get to a full octet. Because once you lose all of your electrons, you expose an inner shell of a full 8. And so this, like, for example, lithium would rather lose 1 electron. But remember, I should keep this color coded. If you lose something that is negative, it's the same as positive. So that's why these 3 are positive. And then carbon and silicon are right in the middle. So both of these are pretty rare, but they can be plus or minus 4. So this is how I knew that magnesium had a +2 charge. It's just based off where it is on the periodic table. Ava, does that make sense?
Yes, thank you.
Of course. Cool. If you have questions about polyatomic ions, I can't really answer them other than just say like, hey, memorize them. There's not too much of any tricks, except for if you see any pair that are ite and 8, the only trick I have is that if you have an ite and an 8, the 8 has one more oxygen than the ite. Other than that, it's just a bunch of memorization. Cool. Okay. Any other questions about number 6? Cool. This is something called Last energy. This only applies to ionic compounds. So that's a good thing to know. That these better all be ionic compounds. And if I could give you a little index card of what to know about lattice energy, it's that number 1, the most important thing about lattice energy is that the bigger the charges get, the bigger the lattice energy gets. And if you're like immediately thinking like mathematically, like, wait a second, is -2 bigger than -1? Or like, how do I keep that straight? If you're like freaking out about the math of it all, it's technically the absolute value of the charges. So like -2 is bigger than -1, but also 2 is bigger than +1. So in case the math is freaking you out, it's technically absolute values of the charges. And the tiebreaker, if you have equivalent charges, number 2, the tiebreaker is the smaller the radius is, the bigger the last energy is. I think we automatically assume with like bigger things are stronger, but in this case, the smaller the thing, the smaller the ion, the stronger it is. But that's like the harder thing for me to pick out. So it's sometimes easy for me to focus on that first. But remember, charges are what matter most. So on this problem, if I was given this on a test, I would go through and make sure I know all the charges of all these ions. then I'd immediately be able to tell, oh yeah, these oxides should have stronger last energy because they're more negative than the chlorides. So like, I'm kind of already down to C or D. Cool. So let's just like use our SAT like logic brain. Let's just figure out which one's the most has the most last energy, and that'll tell us the right answer. So between these two, this one and this one, the smaller the radius, the bigger the last energy is. So like oxide and oxide are tied. So that's obviously not what we're looking at. We're looking at magnesium versus calcium. And I drew this picture to make it obvious. Magnesium is smaller, so therefore it has the bigger lattice energy. That's based off the periodic trend, where the more down and to the left you go on the periodic table, the bigger the radius is. So that's why I would go with the answer D. If there's one other thing I wanted you to know about lattice energy, it's, by the way, let's pick a different color. The bigger the lattice energy gets, the higher the melting and boiling point of ionic compounds. Remember, y'all probably all have just recently learned that as intermolecular forces increase, melting point and boiling point increase. Intermolecular forces apply to molecules, and lattice energy applies to ionic compounds. So don't get mixed up and like at what you need to look at for melting point and boiling point, because it's different if you're ionic or covalent. Also remember that ionics are way higher melting boiling point than covalent. So that's also a good thing to know. Cool. That's kind of the vibe on lattice energy. Does anybody have a question about that? Cool. Sweet. This exam then starts getting to Lewis dot structures and stuff like that, and then the math. So I know some of y'all learned like the math before the Lewis dot structures or whatever. We're not forgetting the math. We'll come back to that. But we start off with question 8. A student drew the following Lewis dot structure for hydrazine. Which of the following statements about this structure is true? So this feels like it's asked about like, hey, is this valid? What blah blah. And so, but I think a lot of people forget about Lewis dot structures. Is to have a good and valid Lewis dot structure, there are only 2 rules. Rule number 1. This one is never broken. It has to have the right number of valence electrons. Now, I say that rule is never broken, but it's not like a static rule. The right number of valence electrons changes for each compound. But what you do is this is why if I'm ever privately tutoring somebody, I make them count the number of valence electrons before even putting anything down on paper. Because I think that when people say, when they first look at a structure, be like, oh, carbon's in the middle, and then they start drawing a skeleton, they've already like, there's a good chance they'll forget to go back and like count the number of valence electrons. So I make all my private students count the number of valence electrons first. There's no exceptions to that rule. I say that because the second rule is the octet rule, and there are exceptions to this rule. So this one's not black and white. Anyways, N2H4 should have 5 times 2 plus 1 times 4 valence electrons. So this should have 14 valence electrons. Everybody cool with that? Or does anybody have a question about where I got that 14 from? All right. So I'm counting up the valence electrons here. 1, 2, 4, 6, 8, 10, 12. All right. It doesn't have the right number of valence electrons. So this is not a valid Lewis dot structure. This is not a valid Lewis dot structure. Sorry. It does obey the octet rule though. So like it's the wrong structure, but like one of the rules are obeyed. And then C, the Lewis dot structure has the correct number of valence electrons. That's false. So at first I was misunderstanding this question, but the answer is B. Does that make sense? I think a lot of people at first, when they're drawing Lewis dot structures, struggled with that rule because they're like, why do I need to add a bond? Why can't I just like put low electron pairs there instead of this extra bond? Which, by the way, this is the right structure, but it's all based off of the number of valence electrons. So you gotta be super confident on that. Anyways, does everybody understand the two basic rules of Lewis dot structure? Wait. Number 9. All right. Number 9, I'm going to take this one slow. And you first might think, crap, the only way to figure this out is to draw their Lewis dot structures. So we can definitely draw their Lewis dot structures. However, I do want you to know what type of atoms can have an expanded octet. Expanded octets can only happen when there's like a nitpicky detail. When it's a central atom and when it's below the second row of the periodic table. There's no central atom here. So the answer is F. Nitrogen is not low enough on the periodic table. Boron is not low enough on the periodic table. And there is no central atom on Cl2 because it's just 2 atoms. So I know the answer is A. But when in doubt, draw the Lewis dot structures. So let's draw a Lewis dot structure. And this will also be a good opportunity for me to like show y'all how I like do this. So let's talk about IF2 negative. Number 1, the most important thing for me is to sum all valence electrons. There's 7. So for IF2, there's 7 plus 7 times 2. And there's a negative sign. So it's plus an extra electron. So there's 22 valence electrons. Step number 2. We call this the skeleton structure. That involves taking a central atom and at first connecting everything with single bonds. I'm going to put my I in the middle. I think a lot of professors say you put the least electronegative thing in the middle. There's some exceptions to that, but that's a pretty good rule of thumb. And this is what I imagine is happening. I know that to have a correct Lewis dot structure, I need to have 22 valence electrons. So I pretend I'm a dealer at a card table and I have 22 cards in my deck, 22 electrons. So now I'm dealing in it. I just dealt out 4 electrons to make those 2 bonds. So now I know I need to put 18 more on this structure. So I like to keep track of all the electrons I've used up off to the side. And when I end up with 0, I know that I've used up all 22 electrons. All right, 3, octet rule. I think you should start with the terminal atoms or the non-central atoms. So to complete their octet, the fluorines with the bond has 2 electrons. But then I need 6 more to complete an octet. So we got 12 electrons left. All right, I'm going to do the same thing to the other fluorine. We have 6 electrons left. I'm going to put 2 sets, so 4 on central atom. I'm going to stop there because I have a full octet, but just know that something's not right. It's not obeying the first rule. This structure only has 20 electrons on it, not 22. I know that because there's 2 electrons left in my deck, right? So step number 4 is what I like to say. I call this the Goldilocks logic. If y'all remember the story of Goldilocks, there's like the porridge that was too hot, too cold, just right. There's the bed that was too firm, too soft, just right. So when it comes to Lewis dot structures, you can have just the right number of valence electron, which to be more informative, that means we use up the correct number of valence electrons, everybody has a happy octet, and we did just single bonds. If that's the case, we're done. We have a valid Lewis dot structure. I should put an asterisk here because just because it's a valid Lewis dot structure doesn't mean it's the best Lewis dot structure. It's just a valid one. All right, number 2, not enough valence electrons. If you don't have enough resources, electrons, to go around, you make people share more. Everybody I've like privately tutored for the last month has heard this analogy like 20 times. If you were babysitting and you have a certain amount of like ice cream sandwiches to give the kids that you were babysitting, and there wasn't enough for each kid to have one, you probably are going to have like a meltdown if you just like ignore one kid and don't give them an ice cream sandwich. You're going to make people share more. And so that's code for you're going to make people share more electrons, aka more bonds. And I will say this is the major indicator of resonance structures. So if that's confusing, we'll talk about that. And then of course, okay, you have just the right amount of valence electrons, not enough. Now the third option is too many valence electrons. You should double check the central atom because if you have too many electrons, it's likely that you're allowed to have an expanded octet. So you double check. Let's go back to like this actual problem. Is I below the second row of the periodic table? And this is the central atom. Yes and yes. So we're literally allowed to just stick the 2 extra electrons on the iodine. So now it has the correct number of valence electrons, and it doesn't follow the octet rule, but it's one of the allowed exceptions to the octet rule. So it kind of checks off the second box. Cool. So in my brain, I want everybody to have like thoughts. If you already have a way that works really well for you to do Lewis dot structures, do what you want to do. But if you are always kind of iffy about Lewis dot structures, here are my 4 steps. Sum of valence electrons, skeleton structure, octet rules, and then the Goldilocks logic. Just the right number, too many, not enough. Cool. So going back to the problem, yeah, IF2- has an expanded octet. And then if you wanted to really prove it to yourself, you could draw the rest of them and say like that they don't have expanded octets. I will say something that I want you to know for this exam is boron's a funny atom. It has a small octet. It just is able to carry or have 6 electrons. So like there's probably going to be a structure somewhere on your test or a question somewhere on your test that has something to do with boron. And you need to know that it does not have a full octet. It's just 6. Cool. All right. So I may have a question about number 9. Okay. Number 10. Same vibe. We're just going to draw them out and see who has resonance structures. So I'm trying to see if there's like a way for you, like number 9, I knew the answer without doing any of the resonance structures because of a weird trick. Number 10, I feel like I'm doing all the Lewis dot structures in my head to figure it out, which takes me about like 5 seconds. So I already know that the answer is C because I like already done all the Lewis dot structures in my head. But let's talk about it from your perspective. If you didn't know what the answer was, you kind of are just stuck with drawing all the Lewis dot structures. So let's start with the first one, ozone. Number one, count up the number of valence electrons, 18. Number two, we've used up 4 of them. Octet rules 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, we just ran out of electrons. And did we have just the right amount? No. The oxygen in the middle is unhappy. It's short 2 electrons. And here's where your brain should go. It says, okay, to make oxygen happy in like an ideal situation, you get 1 more bond. Pause. So like we know we need to add a bond. We need to have 1 more bond with oxygen. But this is where you stop and think, is there more than one right way to do this? Or only one right way to do this? And if there's more than 2 right ways to do it, you have resonance structures. So like somebody might say, hey, I'll take the oxygen on the left, move those lone electron pairs, and get this structure. Does this have the correct number of valence electrons? Yep, it should still have 18. Does everybody have a full octet? Yep, so it's a valid Lewis dot structure. But you also could have just done the other oxygen. So there are 2 valid resonance structures. So that's why A is not the right answer. Now, this also has 18 valence electrons. So it's going to show up and do the exact same thing as ozone. It's just in the middle, there's a nitrogen instead of an oxygen. So I can already tell that for D, it's going to be like O, double bond N, single bond O, or O, and double bond O. So I guess that's sort of a trick, if you can like see that far in advance. Okay. For B, real quick, is anybody not cool if I erase what I have drawn? I'm about to erase it. Okay. B, we have 4 plus 6 times 3 plus 2 valence electrons. So that's 6 times 4, so 24 valence electrons. Carbon in the middle, oxygen, oxygen, oxygen. Doesn't matter that I did like a peace sign with my oxygens. No, you make a T or whatever, it doesn't really matter. You just use up 6 of our electrons for the single bonds. We have 18 left. I add to all my oxygens to make them a full octet, and I just use up all 18 electrons. So pause. I'm 2 electrons short, so that means I need to add. Wait, how did I know I was 2 electrons short? I'm looking at that central carbon, and it does not have a full octet. So therefore, somebody, somewhere, something, that carbon needs 1 more bond. And you should pause and say, is there 1 correct oxygen to double bond, or could I do any of the oxygens? It's any of them. So there are 3 valid Lewis dot structures for this bond. Double bond on the northern oxygen, southwest, or southeast. So it's not B either. The answer is C. That's because when I get done drawing C, it's not going to be the not enough valence electron option. It's going to be just right. Does anybody want me to draw out C? Cool. Okay. Does anyone have a question about Lewis dot structures so far? Let's see. All right. Number 11. Well, let's do number 11, then maybe take a quick break. But when it comes to resonance structures, the resonance structures that I drew on that last problem were kind of all, what's the word? It's equal. They are just like, they look like mirror images of each other. And so not one of those structures was better than the other. But for some molecules, with different resonance structures, some of them are better than the others. And as like a confusing rule of thumb, if the central atom, like sulfur, could handle an expanded octet, I want you to do this formal charge analysis to make sure that you have the best resonance structure. Because sulfur as a central atom, or like phosphorus as a central atom, can be kind of tricky. They can do more than one thing to like make everybody happy. So they're wild cards in my opinion. Anyways, we are about to do a formal charge analysis, which means you need to know two things. Number one, which resonance structure is the best? Well, you want as many zero formal charges as possible. This really isn't what we're aiming for. There are some exceptions to this, but without like going into statistics, this is like the easiest way to say number one. If you're good at statistics, you want the lowest standard deviation of formal charges. But the rule of thumb is as many zeros as possible make you have a low standard deviation. All right. Well, let's say, and like a lot of times you can get where there's all zero formal charges. But what if there has to be a negative or positive formal charge? It's not happy, but it happens. If you have to have a negative formal charge, it's going to want to go on the more electronegative atom option. So if you have like the choice to put the negative formal charge on an oxygen or a carbon, oxygen is going to be more willing to like hold it. And if you have to have a positive formal charge, you're going to want to put it on the less electronegative atom option. So that's the first thing you need to know. Second thing you need to know is how do you figure out formal charge? So any textbook and any professor would say formal charges are equal to the number of valence electrons minus non-bonding electrons minus 1/2 the bonding electrons. This is what most professors say, but here's literally what goes through my head, which just is like a dumb way of saying it, but it works. You take the valence electrons minus dots minus sticks or bonds. So let's talk about A. This oxygen on the west side has 6 valence electrons minus 4 dots minus 2 sticks. So the oxygen has a formal charge of 0. Sulfur has 6 valence electrons minus 2 dots minus 4 sticks. That's also 0. And this oxygen is 0 as well. Is everybody cool with where I got those 3 zeros from? Then I have a question I should ask. If your professor told you like the number of bonding electrons minus 1/2 non-bonding electrons, blah, 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 that is true. That's like the more scientific way of doing it. But if you want like just this easy way of like, oh, dot to sticks, it also works. Cool. So honestly, I would stop there because you can't get any better than 0 formal charges. So like maybe you should like stop and think like, oh, is this a valid Lewis dot structure? So like you should double check that these all have 18 electrons in them. Because when one sulfur and two oxygens, you should have 18 valence electrons. That's 8 plus 2, which is 18. So like I would double check that. And you should double check, is sulfur allowed to have an expanded octet? Because it does in this problem. And the answer is yes, because it's below the second row. These two I would knock out immediately because they didn't have the most electronegative out of the center. And like octet rule. That straight up just doesn't follow the octet rule. But anyways, that's formal charge. Formal charge is the way to tell which resonance structure is best. I think a pitfall and a trap for some folks is to think that the most symmetric resonance structure is always the most stable. It is a coincidence here that the most symmetric one is also the most stable one, but that's all it is. It's a coincidence, not a hard, fast rule. Cool. So we have question about 11 or formal charges. Sweet. All right. We're 1 hour in. And we're making pretty good headway. We're 11 questions in. So we're like a little bit less than halfway through this exam. So I don't feel bad taking a break. They might have any non-chemistry questions, any like weird admin questions for me. Cool. Okay. All right then. I'll pause my audio, but I'll be back. I'm just gonna stretch my legs and walk around. I'll be back in a couple minutes. Okay. All right, everyone. Just making sure my headphones are still working. Can everybody still hear me? Can people hear me? Cool. All right. Cool. So, leading on to some more stuff about bonds. Just this question is all about the fun fact that like you should remember that the more bonds there are, like single to double to triple. Triple bonds are the strongest, but they're the shortest. Single bonds are the longest, so they're the most flimsy or weakest. But usually you think about it the other way around. Like I think it's more intuitive for you to know that single bond's the weakest, so therefore it must be the longest and most flimsy. I guess I kind of said that backwards, but maybe that makes intuitive sense to you. That's like it makes sense in my brain. The thing that's in the back of my head is I think about Shrek for this. I think about the scene where like Donkey's afraid to go over the bridge to the castle because it's like very long and sketchy looking, right? So I think of longer bonds as the weaker ones. That's where my brain's going. So it says, in regard to bond length and bond strength, which statement best describes the carbon oxygen bond in formaldehyde relative to the carbon oxygen bond in methanol? So the bond in formaldehyde is the double bond, so it'd be stronger but shorter. One second, y'all. You hearing that? Y'all, where y'all driving to? Okay, cool. Sweet. Sorry. Okay. Hey, everybody. Don't want to see my baby. Here's my baby.
There he is. Say hi, hi, Dad.
He only had a 30-minute nap, I heard, so he's probably acting funny. Anyways, all right, cool. Sweet. But then we start moving into, before we get into shapes, we start getting into math stuff. So questions like 13 is all that stuff about percent composition and that. But also 14 is going to be empirical formula and molecular formula. So 13, I'm going to take a screenshot of that so I can write it on a different piece of paper. And since we're kind of doing okay on time, I'm going to show y'all both ways on how I would go about solving this. Because I have a feeling the way that it was talked about in class, that's the second way I would choose to do it. I would go about it a different way. So what I think most people were taught was it asked for grams of sulfur, which is just an element, right? But it gives me grams of this whole big old compound. So throw back to like Wick's 5 steps of doing a math problem in chemistry. And it's number 1, is the answer going to be a number that you are supposed to calculate? If the answer is yes, keep on following these steps. Number 2, in every question where there's a number that you have to calculate, there's either a question word or a command word. Determine, calculate, find, or how many or what is, blah, blah, blah. And there is. There's a question word. Number 3, after the question word, in as few as words as possible, you should be able to tell me what we're trying to find. And bonus points if you can tell me the unit. And my answer to number 3 is grams of sulfur. Number 4, is there a formula for grams of sulfur on the back of this test? No. Like, I'm trying to think of a different example from exam 1. Oh, the question was, how much energy is in this photon? There was a formula for that on the back of the test. But grams of sulfur? No. Number 5, is it an extrinsic property? And the answer is yes. So my brain thinks mole math. But I want to teach y'all, I want to first show how I think y'all were taught. You're supposed to also, like, in step number 5, be like, or is there some, like, a red flag going off in your brain? And the red flag I want y'all to know for this exam is if they ask you for an element and give you the mass of the whole compound, or ask for the mass of the compound and give you an element, you can use percent compositions. So percent composition, I want you to think of it as the unit converter between grams of an element and grams of a compound. So once you figure out the percent composition, we can convert. But first, how do you figure out the percent composition? So the percent of sulfur will equal the molar mass of sulfur over the molar mass of the compound. But don't forget that you need to multiply this by number of sulfurs in the atom. So to figure out the percentage of sulfur, we would do, I think sulfur is 32.02. Let's double check that. 5 seconds. No, 3206. But then I need to multiply it by 3. Pause. Does anybody have a question about why I'm multiplying this by 3? Then everybody should know that it's 3 because there's 3 sulfurs there. Okay, sweet. And then, it's kind of nice, they just told me the molar mass of the whole compound. 342.2. All right. Pulling out my calculator. I'm cheating and using a graphing calculator, but I trust that all of y'all can figure this out on the dumb calculators y'all have to use, whatever they're called, scientific. And I get that aluminum sulfate, which is the name of this compound, is 28.1% sulfur by mass. And that doesn't look like a unit converter like you're used to. You've been told that unit converters are grams per mole or whatever. But another way of writing percent, remember, is that there's 28.1 grams of sulfur for every 100 grams of the whole compound. Is everybody confident with what I just wrote in those parentheses? That's what a percent is. It's per every 100. And remember, cent means 100. So it's funny, we're usually so used to doing per every one thing, like per 1 mole or per 1 atom, whatever. It is per 100 because it's a percent. All right, so I have 158 grams of the whole compound. I know for every 100 grams of the compound, we have 28.1 grams of sulfur. Is everybody cool with how I set up that dimensional analysis? So this is multiplication by the percentage also, if you don't want to write it out. 158 times 28.1 divided by 100. And we get 44.4 grams of sulfur. I think the hardest thing that people get tripped up on is well, what if they give me the mass of the sulfur and ask for the whole compound? Remember, you just flip the dimensional analysis, and then that's how you go the other way, which is code for dividing by the percentage if you just rather do that. So I know this isn't part of the question, but people freak out about this. So let's say the question said, hey, there were, so made up example. Let's say in this compound, there was 64.1 grams of sulfur. And the question is, how many grams are there total? Well, in that case, it would just be for every 28.1 grams of sulfur, there's 100 grams of the whole compound. I get that there would have to have been 228.1 grams of the whole compound. Is everybody cool on how I went backwards? It was just like the reciprocal, the flip flop of what I used. Cool. No questions. I am going to show y'all my way of doing this real quick. And if you hate it, forget about it. But if you like it, use it. So still see a couple people writing down, I think. But in a couple seconds, I'll switch pages because I want to show y'all something. Hey, Annalisa, what's up?
Hey, Wit. So I just had a question. So does this only work if it's asking for like grams? Like, it's
Yeah, this is a specific type of question where they ask for grams of an element, but they give you grams of the whole compound, or vice versa. They ask for
okay.
grams of the whole compound, and they give you grams of the element. This
So they
is like,
give you grams. Okay.
yes, and so that's another really point that like I think it's important that when you write grams in the middle of a problem, I want you to always be saying grams of what. So be really specific because those are two different grams. So absolutely. Does that make sense?
Yeah. And I
Cool.
also had a question about the last one we did where it was like, if it was, you said if it was longer, it's weaker. But I was wondering because I was thinking because it had a hydrogen bond, like it would be stronger, but I don't know for sure.
Oh, yeah. So you're starting to blend a couple of topics together. I know exactly what you mean. So this is asking about, Annalisa, this intramolecular force. Intra means within. But if this question was which one has the higher melting point or boiling point, pause. Okay, cool. Sorry, I got a text from the guy whose wedding is tomorrow, so I was making sure I wasn't like supposed to be somewhere. I'm a groomsman in a wedding tomorrow, so that's why I'm like freaking out. Anyways, but yeah, if this question was about who had a higher boiling point, methanol would be stronger because it has stronger intermolecular forces. Good.
Okay,
So
thank you.
You're mixing up a couple things, but you're thinking in the right direction for this. Cool. Good question. All right. Okay, I wanted to show y'all how I would go about this problem. I was telling y'all like what's 5 steps of solving a math problem. And with something being an extrinsic property is asking for grams, I immediately think about the mole math, is what I call this. And they gave me grams of one thing, in this case, sulfur. No, sorry, they gave me grams of the compound. But they wanted grams of sulfur. So you could just do this whole thing as a 3-step unit conversion problem. That's how I would do it. You use the molar mass of the compound first, something called stoichiometry, which is just a ratio of moles to moles, and then molar mass of sulfur. So what I would have done, let me move everything down because we're still going to get that answer in green. It's a different way. If I started off with 158 grams of the compound, we're going to say, all right, I want to figure out how many moles of the compound there are. Well, I know from the question that there's 342.2 grams of compound for every 1 mole of Al2SO4 And here's the stoichiometry part. For every 1 mole of Al2SO4 there are 3 moles of sulfur. Is everybody cool with that new step? It's called stoichiometry. It's a mole to mole ratio. I know that there's 3 moles of sulfur because I looked at the chemical formula and saw that there were 3 acids. And then lastly, for every 1 mole of sulfur, it weighs 32.06 grams. Now, if you're being super observant, you notice, wait a second, aren't those literally the same 3 numbers that you just did in your like percent composition? Yes, it is. But this just like is a different way of coming up with the numbers. So that's what I would do. So therefore, when I plug this in my calculator, I should get the same answer, the 44 or whatever, 158 divide by 324.2 times 3 times 32.06. And 1 second. Let me make sure I plugged in my calculator right. I did not. Cool. Sweet. Now I get 44.4 grams, which makes sense. Or what's the word? Matches. So the second thing I just did was a more generic stoichiometry, molar mass. That logic applies in a lot more cases, which I think is a much more powerful tool. If I were you, I would want tools that work for more situations. But they usually talk about it in terms of percent composition. Does anybody have a question about that? Question. Okay. Cool. 2 different ways of doing it. Number 14, percent. This feels like the exact opposite, but it's actually like the math is pretty different. This is where we take percent compositions and go backwards and figure out the empirical formula. So empirical formula is probably where that got thrown around a lot during the lecture at some point. If you are not confident to explain what empirical formula means to one of your friends, that's an issue. And you should stop and go to ChatGPT and say, can you explain what empirical formula means to me? And if that doesn't make sense, you say, can you explain to me like I'm a middle schooler? Cool. Anyways, for this particular problem, number 14, or any one where you're asked to find the empirical formula, they give you percents and ask to find empirical formula. I do want you to have these 4 steps memorized. Number 1, make it grams, which literally just means rewrite the numbers, but grams. Somebody said this to me for the first time this like semester, and I love this now. So the 4 steps are make it grams, make it moles, divide by smallest, make it whole. Those are the 4 steps of finding empirical formula. Make it grams, make it moles. But to make it moles, you need to divide by the molar mass. 1 mole for every 32.06 grams of sulfur, and 1 mole for every 16 grams of oxygen. So make it grams, make it moles. 87.5 divided by 32.06. And then 12.5 divided by 16. I don't care if you write out all those numbers, but remember, we're not at the end of the problem, so you should not be doing any rounding until the very end. Now, I am a hypocrite because, like, I am rounding for that molar mass. So, like, you pick and choose your battles. So, like, if you want to use the exact numbers on the periodic table for oxygen, go for it. I'm not upset by that. All right, step number 3. Make a grams, make a moles, divide by smallest. This is a trick that usually makes the fractions prettier. And we still can't stop there because we don't have whole numbers. So step 4, make grams, make it moles, divide by smallest, make it whole. You're supposed to be able to look at these common decimals like 0.5, 0.25, and know in the back of your head, oh, I can multiply that by 2 to make it a whole number. So common decimals are 0.25, 0.33, 0.50, 0.66, 0.75. You should know for all of these. Like for a quarter, you multiply by 4. For a third, you multiply by 3. For a half, you multiply by 2. For 2/3, you multiply by 3. For 3/4, you multiply by 4. And that's how you make a whole number. So right now we have S 3.5 for every 1 oxygen. That's almost great. We're just going to multiply by 2, and our answer is S702. Make it grams, make it moles, divide by smallest, make it whole. Cool. Does that make sense? All right. Gives me 30 seconds. Yeah, Lisa.
Hey, Wit, sorry.
You're good.
So with these percentages that you list, what would you do in the case if you got 0.33? Would you just multiply it by 3? Like, how would you, like, seeing these decimals, what is the next step?
Yeah. Let's pretend what I got in red. Let's say instead of 3.50 and 1, we had like 3.33 and 1.
Mm-hmm.
So my point of pointing those out is that like that can easily be made into a whole number by multiplying by a pretty small whole number, and that would be to multiply it by 3 rather than by 2, like we did in this problem.
Mm-hmm.
And if this was 0.25, which is 1/4 or 1/4, I would multiply it by 4 instead of 2 or 3.
Mm-hmm.
Does that make sense?
Yeah, what would you do in the case of like 0.66, like that 2/3?
2/3, you still, the patterns you multiply by the denominator. So 2/3, 6, multiply that by 3 still, it gets rid of the denominator.
Oh, I see.
Yeah,
Okay.
so like in fraction form, this is 1/4, 1/3, 1/2, 2/3, 3/4, and the trick is you multiply by the denominator to get rid of the denominator.
Okay. Thank you.
Yeah, good question. All right. After this, after you figure out the empirical formula, there may be a second problem. They may say, let's say we did all this work, and then they say, they have like another sentence that says, oh, by the way, the molecule has a molar mass of 512.84 grams per mole. What is the molecular formula? So that's not the same as empirical formula. Empirical formula, by definition, has to be the simplest ratio, a whole number ratio of atoms. So there's nothing simpler than 7:2. But not all molecules in existence are the simplest ratio of atoms. Sometimes molecules have 2 hydrogens and 4 oxygens. And like, you don't divide it by 2 for no reason. So what you do is you figure out how much this weighs, aka its molar mass, and you figure out how many times that fits into 512.86. It should be a whole number every time. If it's not a whole number, it means that you probably got the empirical formula wrong. So you take 2 seconds. let's figure out the empirical form, the molar mass of the empirical formula. So in my brain, I'm doing, or not in my brain, in my calculator, I'm doing 32.06 grams for the sulfur, but multiplied by 7, plus 16 grams for the oxygen times 2. And I get the molar mass of this empirical formula would be 256.42 grams per mole. And most of y'all can probably eyeball that. We're saying the molecule is twice as heavy as the empirical formula. Pause. I'll say that again. We're saying that the actual molecule is twice as heavy as the empirical formula. Does anybody have a question on that? So the molecular formula has twice as many atoms as the empirical formula. So the final answer for this molecular formula will be S14O4, which, like, I have no idea if that's a real molecule or not. It seems suspicious that there's so many sulfurs, but like maybe that's a thing. Ah, cool. Is everybody cool with the 2 extra steps to figure out the molecular formula? You find the molar mass of the empirical formula and do the division to figure out how many times bigger it is. Cool. Nobody has any questions? I think we're going to move on to shapes and angles and stuff like that. Cool. All right. When it comes to shapes and angles, aka the Vest curve theory, y'all probably have your own charts, but this is the chart that I have in my mind because I think it's pretty informative, like it's pretty thorough, so I like it. Electron geometries and molecular geometries and bond angles are all based off of this thing called electron domain. Electron domain goes by other names. I actually call it steric number. There's also charge cloud, electron cloud, whatever. All those mean the same thing. It means groups of electrons. So in like octet rule, you're counting up individual electrons. But this one, you're counting up groups of electrons. So it feels different. It's important for you to know that single bonds, double bonds, triple bonds, and lone electron pairs, each one steric number. So a triple bond does not count for 3 steric numbers. It's just 1. That's an easy mistake to make. So 100% of the time, if something has 2 steric number, its electron geometry, its electron geometry is linear. 3 is trig planar. 4 is tetrahedral. Blah, 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 blah. And I will say a lot of this is memorization, but there's sort of this pattern that you're looking for. Like, we can kind of predict what the shapes are going to be. We can kind of predict what the shapes are going to be. Because Vesper theory, valence shell electron pair repulsion. Keyword is repulsion. These groups of electrons are like strangers on an elevator. And like everybody I've probably tutored, I have like showed y'all this analogy before. But like, if we're like looking at a bird's eye view of a round elevator, and somebody was standing here, like, you should think for 2 seconds, if I were to walk into this elevator, where would I stand? And if you said right here, that's exactly what electrons do. They are like strangers on an elevator. And so when there's two people in this elevator, it makes this shape, which if you don't think about it too hard, what I just drew was a line. So the linear shape. Cool. Now, if there's three people in this elevator, the best thing they could do is that. Now, don't forget that this is a round elevator or a flat elevator. So all these people, I say people loosely, these are electron groups, are making a triangle, but this triangle is a flat one. And I'm also stalling because I'm like in the plane. I brought my molecular like model kit, so I'm like trying to make shapes real quick. But this is a flat triangle, and so when you in geometry, when you have a flat space, you call that a plane. So you put the three together. When there's three electron groups, you have a trigonal planar shape. So far, so good. Now, when there's four people in the elevator, you might think, oh, it makes like a box, and they have 90 degrees between themselves. But then, like in this made-up analogy, electrons are not bounded by flat spaces. So instead, you have to think for 2 seconds of a sphere. So if you're good at spatial reasoning, this is going to be easier for you. But think of a sphere, and to get the most space, low-key, I am very happy that all of y'all are writing this down and trying to draw good pictures, but like if this is confusing, just like listen for 2 seconds and like I'll tell you what to memorize, what you need to memorize if this is like confusing. But if you're trying to write it down and understand it, kudos to you. So the first person, if there's four people in this spherical space, somebody would float to the top, somebody would float to the bottom left, somebody would float to the bottom right, but like towards the front of the globe, and somebody would like do the back or the bottom right, but towards the back. In organic chemistry, we write things coming out of the paper with a wedge line and things going like into the paper with this hashed line. And so I'm not the best artist, but what I just tried to draw was this shape. This white line and this white line, sorry, there's a mood going up in this business center of the Hampton Inn. So you can't even, that's a white line, not a blue line. That is like flat. And this sphere is coming out towards you. But meanwhile, this sphere is coming back towards me. And because of that, you can definitely tell based off of this angle right here that this is better than 90 degrees. The electrons get to spread out a little bit more because remember, they're like strangers on an elevator. And you can sit here, we could sit here for about 20 minutes and with some geometry, sine, cosine, tangent, Pythagorean theorem stuff, we could figure out this bond angle. But instead, I just want you to memorize that this is a 109.5 degree angle. Now it doesn't look like it, but this is also 109.5 degrees. You're like, wait a second, wait, that does not look bigger than a right angle. That's because when I hold this up with this angle, do you see how those two, from your perspective, if this was a flat piece of paper, it looks like a very small angle? But if I turned it, you would see all 109 degrees. So like, the point I'm getting at is Lewis dot structures that are on flat pieces of paper are not drawn to scale. So you trust that with steric number, that that's a 109.5 degree angle. So when I show you methane gas, and if I'm drawing a Lewis dot structure, I would draw this. Those are not 90 degree angles. They are 109.5 degree angles. Does that make sense? And that is how they're going to trick somebody who doesn't know about bond angles on the test. Yes, Sydney. Pause. I see that you unmuted, but we still can't hear you yet. It might be like something weird, like audio connected to your phone. That happens to a lot of my students. In the meanwhile, you can also try typing your question in the chat. Here is the chat. If you see that, Sydney. But also, Sydney, if you figure out how to make the audio work, you can also just unmute it. Okay. Does anybody else have any questions while I'm waiting on Sydney to write? Cool. The point I'm trying to make is what I wrote in red, not 90 degrees. It's 109.5. And they'll try to trick you with that on the test. Okay. Cool. Sydney asked, for the tetrahedral ones, do you think it's important to know when the angle is less than 109.5? Yes, that's very important. And I'm going to talk about that. Now, and then there's like a very quick answer, Sydney, to what you just asked. So, when you talk about molecular geometries, you have to focus on more than just steric number. You need to focus on two things, steric number and number of lone electron pairs. And here's my analogy. Let's start with steric number of 3. And like everybody who are probably tutored, y'all have heard this analogy before, and I think it's ridiculous. So I like can't help but like smile at it. But like imagine there's 3 people in an elevator. And we know, oh, that makes like a triangle. And the triangle makes a 120-degree angle between like their points. And that's trig planar, right? Imagine if one of those people were a lone electron pair. Or in my analogy, imagine if one of them became a ghost. All right, so what would happen? Number one, the 2 other people see the ghost in the elevator because it's right there. They're not going to ignore it and then be like, all right, other real person, I want to get 180 degrees from you because I'm more like afraid of personal space with you. No, they're going to kind of like pause and be like, wait a second, there's a ghost here. I'm not going to move in and approach their space. But, so like the ghost is there. But if there's a security camera looking at the situation, I'm kind of mixing up vampires and ghosts, but the security camera would not see the ghost. But the security camera would be like, oh, those 2 strangers are weirdly standing close to each other. Oh, well. So far, does this ridiculous analogy make sense? There's a ghost right here. I'll put them in hashes so you can like actually see them. But like, remember, the security camera can't see the ghost. This is what molecular geometry is. The effect of the lone electron pair is there, but it's not counted in the shape. So we call this shape the bent shape. It is not a straight line anymore. It's a bend or a bent shape. Does that make sense? So molecular geometry, the ghosts are there, but you don't count them as a part of the shape. Now, I can't even like, I don't trust myself drawing steric number 4. Oh, to Sydney's point. Now, reality, if you and I were in an elevator with a ghost, I would probably not mind giving up my personal space with the other person and getting a little bit closer to you so that I could get further away from the ghost. Have you noticed? That means this bond angle, the remaining bond angle, is getting smaller. So Sydney, to your point, when there's a lone electron pair, the angle is less than its ideal bond angle. So this angle is slightly less than 120. Now, like in reality, if like, I'd probably pull like a Scooby-Doo move. If there was a ghost in the elevator, I'd probably like be hugging the other person. But in this analogy, for some reason, we just get like a couple degrees closer to the other person. Like I'm imagining Scooby-Doo like I don't know, like Shaggy jumping into Scooby's arms or something like that. Anyways, so yeah, Sydney, this is when it's less than 120. And I'm not even going to try drawing it. Instead, that's why I brought this. If this northern atom turned into a ghost, this is what it would look like. And if this resembles any famous ancient tombs, you're exactly right. This is what a pyramid looks like. And that is why that's a pyramid shape. Specifically, with the base being a triangle, it's a trigonal pyramidal shape. And then if a second thing became a ghost, we'd be left with this shape, which is still just the bent shape. So you need to know that when you have a steric number of 4, if it's 4 atoms that you're connected to, it's still the tetrahedral shape. But if there's one ghost, it's the pyramid shape. And if there's 2 ghosts, it's just bent. And Sydney, I don't want you to memorize. The only thing I don't like about this PDF or this like picture I stole from the internet, you don't need to know those numbers. You don't need to know 107 and 104.5. I just want you to know that like it's less than 109.5. Sydney, does that make sense? I guess you can type in the chat, say yeah or no. But, so molecular geometries, you have to like start caring about the ghosts. For electron geometries, it's just like point plane. Like 2 is linear, 3 is trigonal planar, 4 is tetrahedral. So you may have a question about that. Ooh. Okay. There are more shapes. Talking about steric number 5 and 6, but let me try to see if it's on these PDFs. You will be given this chart on the exam, which kind of alleviates some of the pressure of understanding and memorizing about steric number 5 and steric number 6. I do want to point out that for some reason, they only include 3 of the molecular shapes for steric number 6. I don't know why. There are 5 shapes it could make. It goes octahedral, square pyramidal, square planar, T-shape, and linear. But maybe they don't want to put that to try like to avoid confusion with how steric number 5 also makes T-shaped and linear shaped things. So I just want to point that out. So if there's a molecular shape that doesn't ring a bell, but like part of our random question, go back on the back of the test and double check if it's not one of the molecular shapes for steric number 5 or steric number 6. Cool. Okay. There's a difference between molecular shapes and electron shapes. You should memorize bond angles and know that bond angles get slightly smaller when you are when you have lone electron pairs. Does anybody have a question about any of that? So for 15, you need to know like Lewis dot structures are going to be very important in this exam because you'll need to know that this Lewis dot structure looks like this. Yeah. And so that is a steric number 4 with 1 ghost on it or 1 lone electron pair. So I know that the molecular shape is trigonal pyramidal. If they asked about the electron shape or electron geometry, the right answer would have been tetrahedral, but that's not what it's asking. Does anybody have a question about 15? Cool. 16. We're starting to get into valence bond theory. And trick number one to valence bond theory is that hybridization is just 100% based off of steric number again. You'll know how in math, when you see an exponent with, or a variable without an exponent, you pretend there's an exponent of 1 there. That's what we're doing here. For a steric number of 2, there's 1s and 1p in the hybridization. For steric number 3, there's 1s and 2 p's. Remember from last exam how there's always only one s orbital and a maximum 3 p orbitals and maximum 5 d orbitals. So for steric number 4, you have 1s and 3p to make 4. For steric number 5, you have 1s, 3p, and 1d. Steric number 6, you have 1s, 3p, and 2d. So that's the connection. And that honestly would probably help you with like 2 questions or maybe 3 questions on this exam. So when I see sp3 hybridization, I know, oh, that's just steric number of 3. And there's 2 shapes you can make when you have a steric number of 3. Trigonal, planar, or backed. Because I have that chart kind of in the back of my brain. That's why I was able to answer that so quickly. So you may have a question about 16. Everybody cool on how I knew that the steric number was 3? Cool. Okay. Ooh. Question 17, I think is a really good question. Because this is like what I mean when I say Lewis dot structures are not drawn to scale. You have to have the whole steric number of Vesper theory in the back of your brain. This says, consider the structure for trifluoroacetic acid. Rank the indicated bond angles from smallest to largest. And so does everybody see for this bond angle 1 that carbon is the central atom? And so you look at this carbon and you like ignore the weird curved arrow for 2 seconds. You say, okay, what's the steric number of that carbon? Steric number of 4, so it probably has a 109 point, let me pick a different color so it's easier to see. That has a 109.5 degree angle. Even though that looks like a 90-degree angle on paper. All right, bond angle 2 is an oxygen, carbon to oxygen. So you look at the central atom, that has a steric number of 3, not 4, it has a steric number of 3. Is everybody confident on why it has a steric number of 3? Yes, double bonds, counter 1. Steric number 3, oh yeah, that's just a third of a circle, so 120 degrees. And then bond angle 3 is carbon, oxygen to hydrogen. So you look at the central atom, which is oxygen, and that also has a steric number of 4. So for a second, you're like, okay, that's also 109.5. But then, to Sydney's point, there are ghosts in these steric numbers. So it's less than 109.5. Because there's, hopefully y'all see the ghosts. I guess this looks like Pac-Man ghosts or whatever. But yeah, cool. Does that make sense? Okay, so 3 is the smallest, followed by 1, followed by 2. That doesn't look right. And they're doing that on purpose. Cool. Does anybody have a question about 17? All right. I want to come back to 18 because I'm not ready to talk about molecular orbital theory yet. I want to talk about the rest of valence bond theory. So it says, there was a drop-down menu on this question. It says, based on valence bond theory, the carbon to nitrogen bond involves the overlap of blank orbital on the carbon and blank orbital on the nitrogen. So like they're kind of nice and they told you, oh, you have to look at the hybridization of the carbon and the nitrogen. But they don't have to tell you that. They just might like point an arrow to a bond and be like, what orbitals cause like this bond? What orbitals overlap? So all you're doing in this question is you're looking at this carbon and looking at this nitrogen. You're figuring out their steric numbers. And remember, steric number tells you hybridization. But this is steric number of 3, so this is sp2. And this is steric number of 4, so this is sp3. sp2, sp3. Those are the answers. Does anybody have a question about 19? All right. For 20, there's 2 more tricks with valence bond theory that I want to do, and then we'll do 20, and then we'll take another short break. But, so tip number 1, steric number determines hybridization. Step number 2, I want you to remember that P's, or anything with an S, makes a sigma bond when it overlaps. And only P's, when they overlap, make pi bonds. So in my head, S's make sigmas, P make pi's. So when an sp3 overlaps with an sp3, because they have S's in them, that's a sigma bond. If an S atomic orbital overlaps with a sp2, that has S's in them. So that makes P's. Oh, sorry, no. That S's make sigmas. And even if, like, we have an sp3 mixed with a p orbital, because there's at least one S in there, it still makes a sigma bond. The only thing that makes a pi bond, remember from last exam when we talked about these are pi bonds? When you have 2 pi bonds next to each other, they don't overlap like, I call that head to head or toe to toe, like all the other bonds. They overlap side to side, kind of weird. And so when you have p orbitals, they overlap like that. And that makes a pi bond. The p's make pi's, s make sigmas. Step number 3, 2 ways I like to talk about this. You can memorize that single bonds, double bonds, and triple bonds. Everything always has 1 sigma in it. But anything above the single is a pi. So like you might say that like double bonds have 1 sigma and 1 pi. And triple bonds have 1 sigma and 2 pi. But another way of saying that same thing is the skeleton structure is made up of all sigmas, and any added bonds are pi's. That is the same thing. So I'm going to show y'all the Lewis dot structure of acetylene real quick. H, C, C, H. That's a single bond. And so if this question asks about how many sigma and how many pi bonds there are, the skeleton is this. So I can tell very quickly that it has 3 sigma bonds. 1, 2, 3. And anything added to it is a pi bond. So we're going to say 2 pi bonds. Does anybody have a question about where I came up with these numbers of sigmas and numbers of pi's? Cool. I would be prepared for that. I'd also be prepared for them to give you like a bigger molecule, and for you to have to complete the Lewis dot structure and tell me how many sigma and pi bonds there are. But the nice thing is, in these big Frankenstein molecules, they give you the skeleton. So without doing anything, you can count up the number of sigma bonds. If I count right, that should have been 8. 1, 2, 3, 4, 5, 6, 7. So there's 8 sigma bonds in this molecule. Now it's up to you to know that this will be a double bond. So there's 1 pi bond in this structure. But that's completing a Lewis-Dot structure and making sure they have 0 formal charges. And we can come back and talk about that if we need more time. Anyways. All right, so that's sort of everything about hybridization, sigma pi, overlapping orbital stuff. We still need to talk about molecular orbital and intermolecular forces. But does anybody have a question about what we talked about the last hour? Cool, sweet. In which case, I'm going to get up and stand around for 2 minutes or 3 minutes. Then we'll come back and finish up this exam and answer any random questions. Does anybody have any non-chemistry questions?
Wait, if I have to leave now to go to class, do I still need to do a review, like post a review on Google to get the recording? For the next
Good question. I would love for you to post a review just because that helps me. But
I'll do it.
okay, but even if you don't do it, I'll still get you a recording. But I would love for you to do it.
Of course. Thank you so
All right.
much.
Yeah, thank you. Cool. Any other random non-chemistry questions? All right. I'm just going to get up and stand around for a bit, but I'll be back. Cool. Can you all hear me? Make sure my headphones are still working. Can anybody hear me? Sweet. Appreciate it, Lauren. Anybody else cool with turning on the camera? That's more people. So yeah, I appreciate it. Cool. Sweet. All right. We got a couple more questions. I'm looking at the wrong document. Let's see. I wanted to go back and talk about 18, which is the molecular orbital diagrams. And I imagine most of your professors taught by the textbook or slides or whatever when it came to this stuff. And it sounds really complicated, in my opinion. It is complicated. But what you need to know is not complicated. Does everybody understand that in order to make an Li2 molecule, you need two lithiums? So far, I'm not saying anything ground shattering. I don't know how to turn that into adjective. I'm not saying anything like super confusing, right? So, go back to the last exam where you were able to do the electron configurations. You might have said that lithium was 1s2, 2s1. Now, in molecular orbital theory, we just focus on the valence electrons, or the things with the highest number before the s, and the p sometimes. So, lithium has one valence electron, and this lithium has one valence electron. So how many electrons are going into the little peach boxes? Well, it's just the sum of those. Or you could think, like, how many valence electrons are in Li2? It's also 2. All right, so that's step number 1. Figuring out how many electrons go into these middle boxes. Step number 2 is you need to know when there's more than one of these boxes, you fill from the bottom, top, and go up. So to fill this in correctly, 1, 2. It's right because it's the right number of valence electrons, and I started at the bottom. So far, so good. Okay. So in my brain, I imagine there to be like a middle, like, what's the word? Equator in this hexagon thing. Anything below the halfway mark is a regular bonding orbital. They don't have asterisks. The jobs of these electrons that are below the halfway mark are to build bonds, just like we would normally say. But the electrons that are higher in energy, or in the top half of the hexagon, are anti-bonding electrons. Their whole job is to cancel out the bonding electrons and inherently, like, destroy the bond. And there are none of them in this picture. So the answer to the 2 questions to this thing is how many electrons occupy valence molecular orbitals. That's the middle stuff. There's 2 electrons. And then I asked how many electrons occupy the sigma anti-2s molecular orbital. That's the thing on the top. And the answer is 0 of them. No electrons are in there. So that's the answer here. There are 0 electrons in the anti-bonding orbital. They just didn't get that hard. They didn't get that high because there were only 2 electrons in there. So the 5 questions they might ask are: number 1, how many valence electrons are there? Or how many occupy valence molecular orbitals? Number 2, how many of them are bonding? That's in the lower half, so the answer to that would have been 2 of them are bonding. How many of them are anti-bonding? Well, that was 0 because none of them made it to the top half. Number 4, what is the bond order? And the formula for bond order is, it makes sense when you know what's happening too. Formula for bond order is number of bonding electrons minus non-bonding electrons over 2. So like if the job of a non-bonding electron is to like cancel out a bonding electron, they subtract. And then don't forget that it takes 2 electrons to make a bond. So that's why we divide by 2 to get the number of bonds. So if there were like 2 electrons left over who want to make a bond, that makes 1 bond. If there are 4, that'd make 2 bonds, and so on. Now, because of that formula, it is acceptable and okay to have like a halfway, a half bond. So like 1.5 or 2.5. That sometimes happens. That's okay. Cool. So, there was a 5th question. Some people have heard of these words based off who I've tutored the last 2 weeks. Some people haven't. There's 2 vocabulary words: diamagnetic and paramagnetic. If you look at a molecular orbital diagram, if there are 0 unpaired electrons, like in this case, each red has a pair, it's diamagnetic. If there's 1 or greater unpaired electron, it is paramagnetic. Cool. Does that make sense? Like, that's just a new vocabulary word. I don't know if y'all need to know that or not, but I'm just out there to cover my bases. Another example of this same exact problem would be a question like 20. Now, it doesn't look the same, but it is the same because it's like 2s, 2s. They just didn't draw the hexagon looking thing, but it's there. So when you're making O2, 2 negative, that's when you have an O minus and an O minus on either side. So pause and think to yourself, how many electrons are in an O with a minus sign? Remember, minus means extra electron. This has 6 valence electrons. O and minus should have 7. If I have 7 coming from the left and 7 coming from the right, there should be 14 arrows in this molecular orbital diagram. And there are. Cool. Now, I will say, when P's overlap, 2 P's, you don't need to write all this out. I'm just like giving y'all context. Again, we start from the, like they've already filled in this chart for us. It starts from the bottom and it filled up. And below the halfway mark, let me get out my green highlighter. Those don't have asterisks. So those are bonding electrons. And you notice above the halfway mark, those do have asterisks. So those are anti-bonding electrons. Is everybody cool so far? It still follows the rules, but they've like filled in this diagram for us. There are 14 electrons and they start from the bond filled up. Now the bond order is number of bonding electrons minus non-bonding electrons divided by 2. Now you do need to look at both hexagons simultaneously, but if you've always noticed that you could get the right answer by just looking at the top hexagon, you're correct. So I'm going to do it the technically correct way, but if you have a trick around, then it's fine. So the number of bonding electrons is 6 plus 2. So 8. 8 bonding electrons. Does anybody have a question so far about where I got the 8 from? All right. anti-bonding electrons? 6. Everybody cool with where the 6 comes from? Divide by 2, because you always divide by 2. 8 minus 6, 2. Divide by 2. The correct answer should be bond order of 1. Cool. And then the second question was, there are a blank number of unpaired electrons in this ion. 0. Everything has a pair. So that would be diamagnetic as well. Cool. Honestly, that's what I want you to know with molecular orbital diagram. That you take the atoms from the left, atoms from the right, and that's how many arrows should be in there. And you start from the bottom and fill up. Cool. Does anybody have a question? I imagine I explained this more simply than what your professors, how your professor explained that. But I'm pretty sure in my sort of simplification, I hit on everything that they usually ask about. No questions. We'll probably start moving on to, let's see, intermolecular forces. Now, I'm looking at question 21, and this is still from the old stuff, so we'll do this one real quick. Steric number of 2, so SP. Steric number of 4, so SP3. Anyone have a question about 21? Okay. Before, let's see. That's why I'm being all confused. I'm looking at wrong exams because that was 2023. Let's go back to 2022. 2022, it then starts off with saying, hey, what are polar and non-polar molecules? And this is important for intermolecular forces. Now, to determine if a molecule is polar or non-polar, I'm not talking about polar bond or non-polar bond. I'm talking about the whole molecule. And sometimes even things with polar bonds do not make a polar molecule. It's all about if the molecule is asymmetric or symmetric, which kind of is based off their shape. Now, there's no way of getting around it, but you should draw the Lewis dot structure for these. But here are the two questions that are in my brain that help me determine if something's polar or non-polar. Does the central atom have a lone electron pair? The answer is yes. Polar. If the answer is no, it's probably a symmetric shape, but there's one other way. Are all non-central atoms identical? If this answer is yes, it's non-polar. This answer is no, it's polar. This works 100% of the time for normal octets and works like 80% of the time for expanded octets. So it's a pretty good rule of like this line of logic is pretty good. So O2 looks like this. There is no central atom. So no, the central atom doesn't have a lone electron pair. Are all non-central atoms identical? Yes. So that is non-polar. All right, carbon dioxide. Does the central atom have a lone electron pair? No. Are the terminal atoms identical? Yes. This is also non-polar. Sulfur dioxide. I think we've already talked about this shape, but the best shape for SO2 looks like this. I think the best shape has a lone electron pair. It is polar. And that's how I would tell pretty quickly that only SO2 is the polar molecule here. Now, you do have to like be good at drawing loose dot structure, or else this is going to be tough. But once you draw loose dot structures, with my line of logic, I want this to be pretty simple. Oh, do we have any questions? Okay,
Yeah, so random question. Like, so for like CO2, what if I accidentally made like a triple bond and then a single bond? Like, how would I know? Like, then I wouldn't get the right answer. So how would I like know?
you would still get the right answer. Well, I want to prove it to you. And Lisa, does the central carbon have a lone electron pair?
Oh no.
Are the two terminal atoms identical?
No.
Are they both oxygen, or is one not oxygen?
Both are oxygen.
Good, so they are identical atoms.
So
So
yes.
it's still, so the point I wanted to make that you just brought up is, to me, you kind of just asked, what if I draw a different resonance structure? And the answer is different resonance structures should not affect steric number or number of lone electron pairs. So that just covered a ton of things. Different resonance structures should have the same polarity, same electron geometry, same bond angle, same number of sigma and pi bonds, and the same, I forgot one, maybe molecular geometry. So to answer your question, different resonance structures should have a lot of the same attributes.
Okay.
Cool. Great question. Cool. So then we start getting to the intermolecular forces. And just as a recap, most of today, we've been talking about intramolecular forces. It's important that you remember that intra means within. These are forces within molecules, mostly covalent bonds. But I guess I'd also include ionic bonds in this category. In general, both of these are ionic and covalent, are much stronger than this new thing called intermolecular forces, which inter means between. So I remember in high school biology, which was also the last time I took biology. So I always say to everybody that I tutor, y'all probably know more biology than I do. But the last time I took biology, there was a chapter about water. I remember in water, when we talk about water, we talk about how it's adhesive, cohesive, capillary action, and something else, or maybe osmosis or something. But because of chemistry, water is cohesive. That means it likes to stick to each other. That's because when this H2O is floating around here and this H2O is floating around right here, there's an attractive force between them. And when we try to categorize it, there's actually several of those forces in water in particular. But I do want you to know that if you're comparing intra to inter, these are stronger. In case they hit you with a conceptual question about that. But to talk more about intermolecular forces, from weakest to strongest, you need to know about London dispersion forces, dipole-dipole forces, also known as dipole-dipole interactions, hydrogen bonding, and ion dipole, or ID. Hopefully all four of those sound familiar to you. I would say that for these three, or sorry, for these four, you need to know three things. Maybe less so the first thing, but as a good chemistry student, I would recommend that you know an explanation and the definition of all four of these. And like I've said like 2 times already, if you can't describe London dispersion forces to your friend, I would just sit down with ChatGPT and have it explain it to you. So that's the first thing I would know. Number two, and this is where like if application and problems start coming in, you need to be able to look at a molecule such as H2O and say what H2O is capable of. And I know that H2O is capable of LDFs, DDs, and HBs, but not IDs. Why? Well, here's the rundown. All molecules are capable of London dispersion forces. That's because London dispersion forces are due to a randomly moving electron. And when you stop and think about it, everything has electrons, and all electrons are moving around randomly. So literally everything has London dispersion forces. That's the logic there. Now, the reason why we spent 5 minutes talking about polar and non-polar things is because only polar molecules are capable of dipole-dipole forces. And hydrogen bonding is kind of funny. I just like dived in and said like, all right, there's intramolecular forces and intermolecular forces. They're not the same thing. But to determine if something is capable of hydrogen bonding, you actually look at the covalent bonds, which are the intra. And only molecules that have a hydrogen covalently bonded to a fluorine, an oxygen, or a nitrogen are capable of hydrogen bonding. So it is not good enough or enough to just have hydrogens. Not everything that have hydrogens in them are capable of hydrogen bonding. That is not the only criteria. But if it doesn't have a hydrogen, it's automatically incapable of hydrogen bonding. So it kind of works the other way. Cool. So in these three examples, if I have a bucket of water, for example, there's not one water molecule, there's a ton of them. And like these forces can occur in a pure substance. Remember, pure means every molecule is the same. The opposite of pure substance is a mixture. And that's why ion dipole forces don't get brought up that much, because there's two halves of it. For an ion dipole connection, you need an ionic thing and a dipole thing. Well, ions are from ionic bonds, and polar dipoles are from covalent molecular structures. So something can't be both a polar molecule and an ion. So for that reason, this one kind of sticks out. You need a mixture of ions and polar molecules. So this one would kind of stick out on a test because like usually they just tell you a chemical. But if they want to bring up something with ion dipole, they would have to say NaCl mixed with water, or potassium bromide mixed with methanol. And like it just kind of sticks out. So there's not a lot of questions that involve ion dipoles. But I say that, and this semester might be one of those semesters that involve it, so we need to talk about it. Okay. So that's the main thing, which is identifying them. Let's see if we can go answer this question. It won't help us with 22, but it does kind of help us with 25. 25 says, what kinds of intermolecular forces must be overcome when elemental iodine had two sublimes? This is just a really weird and overly complicated way of saying what intermolecular forces does I2 have? Remember that sublimation is when a solid turns straight into a gas. And to go from a solid to a liquid to a gas, you're breaking apart the intermolecular forces. So that's what it means by to overcome them. You're breaking them. So once you get past that, you're just like, okay, I2. Is it a molecule? Yeah. So it has London dispersion forces. Is it a polar molecule? No. So it does not have dipole-dipole interactions. Are there even hydrogens in I2? No. So it only has London dispersion forces. Does 25 make sense? Let's go back and talk about these. There are some situations where I would want you to know who has more of LDF or dipole-dipole. Because if I had two molecules, I'm being super generic. Let's say molecule A and molecule B. And let's say both of them are capable of the first three. And the question asks, who has more intermolecular forces? You go to the strongest one, hydrogen bonding, and you try to decide who has more of them. Or if something had just London dispersion forces. And the question was, who has more intermolecular forces or stronger one? You go to LDF and you see who has more of them. So another thing that you need to know is sort of how to judge who has more, who has less of something. For London dispersion forces, as contact surface area goes up, so flatter, skinnier, longer molecules are capable of rubbing against other molecules more, and that rubbing causes London dispersion forces. But that's how I like to do that. So as surface area goes up, LDF goes up. Dipole. I think it's pretty hard for me to point blank look at a molecule and tell who's more polar or less polar, except for one case. That case usually comes up. Alcohols. In general, I'm going to give you the rule and then I'm going to explain it. The shorter the tail of an alcohol, the more polar it is. So it's capable of more dipole-dipole forces. But to understand that, you need to understand what an alcohol is. An alcohol in chemistry is a hydrocarbon chain. Hydrocarbon, meaning hydrogen and carbons, with an OH at the end. So that's an alcohol. It's called propanol. But this is also an alcohol. This is called ethanol. And this is alcohol. Now, both of these have a very polar region near those lone electron pairs on the oxygen. But the rest of it is called the non-polar tail. And so the less of a non-polar tail it has, the more and more concentrated the polarity is. I've yet to figure out I haven't sat down and thought about a great analogy for that, but it's just all about proportions. Proportionally, I would say more of this molecule is polar than non-polar. So therefore, this one is more polar. Does that make sense when I'm talking about these alcohols and those hydrocarbon tails? Cool. Okay. Hydrogen bonding. I think there's a bit of a hierarchy. The bigger difference in electronegativity is slightly more powerful when it comes to hydrogen bonding. So HF is a little bit stronger than HO, and it's a little bit stronger than HN. But more importantly, the number of hydrogen bonding sites is a big indicator. So if I had methanol, which looks like this, and water, which looks like this, water has two OHs in it, and methanol just has one. So this one has more hydrogen bonding. That's how I judge who has more hydrogen bonding. It's probably like number of hydrogen bonding sites. And then ion dipole, I don't think I've ever like seen a question that talks about that, but I guess like the more polar and the stronger the ions are, the more ion dipole there is. So like a +3 charge is stronger than a +1 charge or something like that. So after you talk about that, the applications of intermolecular forces are two. Remember, this only applies to molecules, not ionic compounds. But as intermolecular forces increase, the melting point and the boiling point increase. But in case they try to trick you, there's two more words I want you to know. Surface tension and viscosity. Those are two other physical properties of solutions or chemicals. And the higher those intermolecular forces are, it also increases surface tension of a substance and its viscosity. Cool. The second application is solubility. And we like to say that's likes dissolve likes. I remember seeing that in biology in high school, where I think biology they talked about how like polar things like to dissolve polar things, and non-polar things like to like mix with non-polar things. That's true, but we just add more to it. Things that are capable of hydrogen bonding are more likely to dissolve things that are capable of hydrogen bonding, because they're going to be stickier and want to mix with each other more. So, example would be like, let's say we have a solvent, molecule A and molecule B. And let's say the solvent is capable of London dispersion forces and dipole-dipole forces. And let's say molecule A is capable of London dispersion forces and dipole-dipoles. Molecule B is only capable of London dispersion forces. And the question says, which one is more likely to dissolve in the solvent? It's going to be A, because it has more things in common with the solvent. Cool. Does that make sense? So that, I believe, is going to help us with these remaining questions. It says the following compounds have similar molar masses. Rank them in order of increasing boiling points. That whole sentence about these molecules have similar molar masses matters in the real world, but like y'all might not have noticed that you needed it. I went on and said that London dispersion forces are the weakest force, but some molecules are so long and have so much surface area that the London dispersion forces keep on accumulating and become like overpowering. Ethylene glycol or car antifreeze has super duper long chains of molecules, so it has like an incredible amount of London dispersion forces, and that's why it's such a viscous fluid. It means it like pours really slowly, like syrup or honey. So if you didn't catch anything from the similar molar masses, this is a rare case where that wouldn't hurt you. Anyways, increasing boiling point is code for increasing IMFs. So a non-polar covalent compound is only capable of LDF. A polar covalent compound capable of hydrogen bonding can do LDF, DD, and HB. And then compound number 3, a polar covalent compound that cannot form hydrogen bonds. Well, that just does London dispersion forces and dipole dipoles. So from lowest to highest, it go 1, 3, 2. Sweet. Does that make sense? Let's see. Anybody have any questions about that? All right. 24. I think 24 is kind of mean. I would have gotten this wrong. But 24 is, I would have gotten the first part right. Which alcohol is more soluble in water? Well, water has LDF, dipole, dipole, and hydrogen bonding. So first we say, okay, both of these things have hydrogen bonding. So like that's kind of a dead tie. But water is very polar. So the more polar one is more likely to mix. And this one is more polar because it has a shorter tail. So for that reason, this one, the methanol, is more likely to mix with water. And I'll be honest, I would have screwed up part 2. I would have said that because methanol is more polar, it has a higher boiling point. But these two things do not have similar molar masses. This one's like 80% more. And this is what I mean by London dispersion forces start to accumulate to be very large. So even though I've told you that London dispersion forces are the weakest force, this one has a ton of them because it's a very long, skinny molecule or long analog contact area. So it turns out the butanol has more intermolecular forces in general. So it would have the higher boiling point. I probably would have gotten this wrong on the exam. Somebody's asked me this question recently, so it's on the top of my brain. So you might be thinking, wait, how do I not get it wrong on an exam? What is sort of the threshold for how long something is to make it so London dispersion forces start like being too much? And unfortunately, I don't have a good answer for that. I'm not exactly sure. So I would hope that enough people get this question wrong where they just give back credit. So, because I don't have a great answer for that. So that's kind of it's almost a very lame point to end. No, it is. That's a very lame point to end this whole talk, that I don't have a good explanation for that one question. But like, I sort of explained it, but I don't have a good like rule of thumb for you to use during the exam. And 26. Does this type of graph look familiar to any of y'all? I've seen no from Lauren. No, cool. I have a feeling this is something that they talked about that year, but y'all didn't get a chance to talk about. I think most of the time they leave this out in Clemson chemistry now. They don't talk about it in chemistry 1 or in chemistry 2, unless you have Dr. Schwanevelt for chemistry 2. Side note, if any of y'all take chemistry 2, and you have Dr. Schwanevelt for it, he does his own thing and like gives his students his own exam, which is very hard to tutor. So I don't actually really like tutoring Schwanevelt's student, but I'll do it. Anyways, cool. You got through that exam. I don't have a list of like objective, or maybe somebody's texting me them, but I don't have a list of all the objectives for the fall 2025 exam. So does anybody realize, or does anybody recognize if there's any like questions I totally left out? And like for y'all who like came late, I'll be able to get you a recording. So I know y'all can't answer because y'all don't know exactly what I talked about. But for the people who've been here the whole time, you feel like there's anything that maybe I straight up left off something, or is there anything that we have like 15 more minutes? Anything that like people would want a better explanation of?
I have like the objectives that Schroeder gave us, and it says electrostatic potential.
Interesting. That feels a lot like lattice energy. So, lattice energy is all based off of Coulomb's law, where electrostatic force is equal to Coulomb's constant, which you don't need to know. Honestly, I don't feel like you need to know this anyway. But Coulomb's law is all about charge 1 times charge 2 over their distance squared. And this is where we get lattice energy from. Remember how I said that how lattice energy gets bigger as the charges increase, but gets smaller as the distance increases? It's based off of electrostatic force potential. But what I want you to know about electrostatic forces, and this is probably something you've like experienced in like playing with a fridge magnet before. The stronger the magnet, aka the charge, the stronger it wants to attract each other. And the closer the magnets are to each other, the stronger the potential or like attraction is. Kelsey, does that make sense?
Yeah.
Cool. So think about fridge magnets for that. Stronger magnets means more potential, more attraction, and closer magnets mean more potential or more attraction. Cool. Anything else, Kelsey, on the objective list that sounded interesting?
I'm looking at it right now.
All good, all good. And while Kelsey's looking, anything else? Anybody else have any random questions?
Could we do like maybe 1 or 2 more of like the math ones?
Yeah.
With, like circle formula and like percent composition.
Totally. Let's do this one from 2023. And it says, so this one like gives you everything. It gives the percent composition and the molecular mass of fentanyl. So we have to figure out fentanyl's molecular formula. The 4 steps, even if it's asking for the molecular formula, we need to go through the empirical formula first. So the 4 steps are make it grams, make it moles, divide by smallest, make it whole. So we're starting off with 78.53 grams of carbon, 8.39 grams of hydrogen, 8.33 grams of nitrogen, 4.67 grams of oxygen. We're going to divide this one by 12, 1.01, 14, 16. As we're doing step number 2, which is make it moles. And those are all the molar masses. And you don't have to have those memorized. You just go to the periodic table to figure them out. So 78.53. I'm going to do these all on my calculator real quick. So I get 654,830,7.595.2975. Step number 3, divide by smallest. And I get something kind of like, I'm getting ridiculously big stuff, but we're just going to trust the process. I get 22 carbon. Divided by 0.29. I get 28 hydrogen. 2 nitrogen, and 1 oxygen. Just because that's a weirdly large number, I'm double checking the answer key so far and see if I agree with it. Cool. Yeah. I should have trusted my gut. So far, so good. And then step number 4 is make it whole. Nice thing is like these are already whole numbers. So this doesn't give us the molecular formula. It gives us the empirical formula. C22, H28, N2O. And now we got to figure out the molar mass of that. So I'm like, in my calculator, I'm doing 22 times 12 plus 28 times 1 plus 14 times 2 plus 16. And that roughly weighs 336 grams per mole. And guess what? That's how many times does 336 go into 336.417? About 1 time. So we multiply it by 1, and that actually, in this case, is the molecular formula. So 22, 28, sorry, I screwed up, 28 to 1. Lauren, does that make sense? Good. Does anybody else have a question about this problem about fentanyl?
So if the molecular mass was like doubled or tripled, you would just multiply it to find it, and then multiply the subscripts.
Yeah. If they had said fentanyl's molar mass was 672 grams per mole, you would have been like, oh, that fits in twice. So it's 44 carbons and 56 hydrogens and blah, blah, blah.
Okay, got it.
Yeah, of course. Kelsey, still anything looking weird on the objective list or not really?
I think most of the stuff looks normal. There's just like a list of words we need to, it says define and use these terms, and I haven't seen a lot of them before, but besides that.
Oh, do you mind reading off a couple of them?
Yeah. There's vapor pressure, evaporation, polarizability, temporary dipole, dipole moment, permanent dipole.
Good. Almost all of those have to deal with the intermolecular forces. I can never say that word. Polarizability is how, if I put a magnet or an electrical current near an atom, how much will the electrons all run to one side and make a temporary positive and negative side, which is a temporary dipole. And a permanent dipole is what we call a dipole or polar molecule. So most of those have to deal with London dispersion forces. So if you need to, I would go like try to look up something online that describes London dispersion forces a little bit better. Take the 5 minutes to read up. Now, I was a little surprised that there's a question on vapor or the words vapor pressure and evaporation rate. In case you need to know this. Now, vapor pressure is something that's pretty hard to define, and I invite you to go to ChatGPT and have it explain to you to the level that you need it. But one thing I will throw in here that I didn't know I need to do, go back to what I said about intermolecular forces. As intermolecular forces increase, it increases the melting point, boiling point, and surface tension and viscosity molecules. But in case they ask this, an increase in intermolecular forces decreases the vapor pressure. So it's something that has a lot of intermolecular forces have a very low vapor pressure. Cool. So I'm not sure if you'll need to know that. Usually that's a chemistry 2 question, but good to know. Yeah, Annalisa.
So I was looking at the objectives for me, and it was like it bolded this one. So I was just wondering. So the objective says combine the concepts of valence bond theory and molecular orbital theory to explain resonant hybrids and the delocalization of electrons. So I was wondering, like, what are the differences between the valence bond and molecular orbital, and then like how would that explain resonance hybrids?
Yeah. I think the biggest difference that comes to my brain is that, like, in valence bond theory, we say that, like, all electrons are trying to make bonds. And let's say, yeah, valence bond theory, everybody is trying to make a bond. In molecular orbital theory, some of them are anti-electrons. Some of the electrons are, their whole job is to sabotage. Different, but I'll be honest, I'm going to Google to figure out how it explains resonance structure difference between BBT and MOT. Google says valence bond theory describes bonds as very localized. Like, there's one little place in space that they overlap. While molecular orbital theory describes bonds as delocalized molecular orbitals that spread out across the entire molecule. Okay, so I didn't really get into like drawing valence bond theory, but like if I had a very simple molecule like formaldehyde, what valence bond theory says is, okay, we have a carbon who has these three hybrid orbitals, an H, an H, and an O, who also has three hybrid orbitals. And so you would think that the two electrons between oxygen and carbon are right there, right in between those two overlaps. But in real life, they're not right there. They're still like all over the place. They're bouncing around. So molecular orbitals do a better job of just explaining how things aren't in one spot. They're delocalized. They can float around. Does that make sense?
Yeah. So is that why, like, you know, the whole sigma pi, like pi is like you said, it's like right next to each other. It's talking about a specific area that it's
Yeah,
bonded.
that's very, very localized. But like in
Okay.
real life, like especially like a pi bond, you might say like, oh, I see exactly where those two are overlapping. That little sliver there. But like a pi bond doesn't, like, not only is it not in those two slivers, but like, remember in resonance structures, the pi bond can like be over here and then like switch over here. And so like they're definitely not stapled down in one place. They're kind of all over the place.
Okay.
Does that make sense?
Yeah. Thank you.
Yeah, of course. I have never seen a Clemson question go in depth on that. But who knows? This could be the semester. But yeah, cool. We just have a couple more minutes. Does anybody have any last second questions for me?
Really quickly, could you go back to the other exam?
The
The one-
2023, the one we did less of?
Yeah, and then question 16, like just for clarification.
Boom. That's like, does octahedral electron geometry ring a bell, Lauren?
For the, I mean, a little bit.
And if it didn't, I'd hope that you like go to the back of the test and be like, oh, octahedral,
Yeah.
steric number of 6. And so to do this question, you would have to draw the loose dot structures and figure out who has a steric number of 6.
Okay. Perfect. I
Which,
said, sure.
yeah, which I believe is 2 of them. I think A and B have 6 steric numbers. Definitely B. I can tell because there's 6 fluorines. But I think the iodine in A also has a lone electron pair.
Okay.
Cool. Sweet.
Thank you.
Yeah, of course, of course. All right. Any last second, very pressing questions? If not, I'll sign off and go celebrate wedding festivities, and while y'all are stuck in something studying chemistry. But I will be next to my phone. So if any of y'all have my phone number and want to ask me chemistry questions, I'm sure there'll be downtime. that I can answer questions. But if I don't hear from y'all or you individually, good luck studying this weekend. Text me if you need me. Email me if you need me. I'll send out the recording tonight, depending on the rehearsal dinner, or maybe tomorrow. And yeah, good luck on the exam. I appreciate y'all for being here.
Thank you.
Of
Thank
course,
you,
y'all.
Whit. Bye bye.
Thank you.
Bye. See y'all.